Okay, so Google Bigtable, again, had a lot of influence, and one of the major outcomes is just like MapReduce, it was taken up and implemented as an open source project called HBase. And so where Bigtable was compatible with MapReduce, HBase was compatible with Hadoop. And in one slide, there's not much difference here, but I just want to mention the terminology so you've seen it. That there's table at the top level, and then region, store, and then memstore and store file. And so the exact names of these structures are a little bit different, and they did insert one more layer of abstraction, which is this region. Fine. And then how this sort of is compatible with MapReduce is that each one of your map functions will process a single tablet, and so it's sort of one-to-one with the blocks of data that we talked about when we talked about MapReduce. And then I just sort of ask this question, sort of open-ended, is that there's this notion of speculative execution in MapReduce that we talked about, whereby for fault tolerance reasons, it might kick off the same map task twice on two different replicas of the data. And the reason for this is that if one fails, well, you have the other one, right? So you don't have to start over from scratch. But in this environment where you're now working on data that is being actively updated, and that's what HBase and Bigtable are designed to support is updates, it's not quite as clear to me what's going to happen when you have, it's possible because of eventual consistency that these two tablets will not always agree instantly. On the same record they'll agree, but different records within the tablet may not. Okay, and so just an example of when you sort of mix these two systems and there are no sort of system-wide transactional guarantees or system-wide even properties, that you can run into trouble. And I think that a general theme here with these sort of NoSQL systems, including the ones implemented, designed by Google, is that you're kind of offloading some of this responsibility to the application, to the programmer, to sort of sort this out and make sure it's okay. Okay, and we're going to come back to that in just a couple of minutes. All right. So after Bigtable, several years later, there's a paper by a bunch of folks at Google about a system called Megastore that I'm not going to spend a lot of time on, but it's basically, they found this point I sort of just made, is that these loose consistency models can complicate application programming. And what they wanted to do is provide a little more system support for certain kinds of safe updates. Okay, so here, instead of full transactions being safe within an individual record, as they are in Bigtable, they've extended it with this notion of entity groups. And so an entity group, which should be on this slide, and an entity group is a set of records that tend to go together, tend to be accessed together. Okay. So maybe, again, this is the blog and all of its comments, for example. Each one of these is a record because it's an extensible record store, so it's okay for them to have different schemas. But they all tend to go together. Okay. And so what they've done is extend transaction support over an entire entity group, a set of related records. Okay, so they still get the scalability by not requiring full system-wide global, synchrony, but they allow you to sort of they get away from this problem of, very frequently I might need to update one record and then update all of its sort of children records at the same time, and I can't do that in any kind of safe way. Okay, so fine. Fast forward one more year, and so there's a 2012 paper on a system called Spanner, and I just want to mention these quotes, and then we'll talk a little bit about the system. And this one is still sort of being explored by the community. It's not available actually for use, but the paper is being explored and the idea is being explored. So, for example, you don't see an open source. Actually, yeah, that's not true. You do see there has been a couple open source implementations of the ideas in Spanner, but they're not quite as popular as some of the open source implementations of the other Google systems. Okay, so it says even though many projects happily use Bigtable, we've also consistently received complaints from users of Bigtable. It can be difficult to use for certain kinds of applications. Those that have complex evolving schemas, or those that want strong consistency in the presence of wide area replication. Okay. And so then they go on to say, we believe it is better to have application programmers deal with performance problems due to overuse of transactions as bottlenecks arise, rather than always coding around the lack of transactions. And so this, the database community could have said, well, sure, well, duh, right? That's exactly the point, is that system supplied support for transactions is always a win, right? Because it's difficult, error prone, and expensive to try to do this at the application level. And more importantly, it's fundamentally wrong in some sense to do it at the application level, because the application doesn't have global knowledge of what's going on, right? Only the system does. So fine. So although Spanner is scalable in the number of nodes, the final quote here, the node local data structures have relatively poor performance on complex SQL queries because they were designed for simple key value accesses. And then mentioned algorithms and data structures from the database literature could improve single node performance a great deal. Again, it's somewhat of a Google style approach to the problem of reboot everything, rebuild it all from scratch, and then sort of cherry pick and bring things in. So this has been working pretty well, and they have fantastic impact in the community. But there's a lot out there in the database literature and in database systems that could have been used from the start. I mean, in fact, trying to start from the beginning and just say we're going to build a big Google-style parallel database may have been a good choice, rather than sort of getting completely away from it and then coming back incrementally and finding yourself in a SQL system. Now, I sort of skipped over what Spanner is, but it's planet-scale database system. There is a SQL-like language. Well, actually, let's go back to our. I know what I'm missing. I'm missing our table here. Let me flip back a few. So here it is down here. So I'm missing the slide here where I showed it. So really big scale. Primary accesses you can access by other attributes. There are transactions, and in fact they're global this time. They're real ACID transactions. It's not clear to me whether joins are supported. I suspect they are because they keep talking about SQL, but I couldn't find an example of whether it is or not. There is some notion of schema, and they do sort of protect against data that doesn't conform to the schema. There is some notion of logical data independence, although they don't talk about it much. There is a SQL-like declarative language on top of it. I didn't see much evidence that they're doing a whole lot of fancy optimization, and I did just show you that quote of where they say that their performance is sort of poor on complex analytic queries. But that's something that probably could come along somewhat quickly. Okay. So fine. So that's Spanner at a high level. Let me give you a couple more details about what the system does. So the data model here is this notion of directories. And these are a set of contiguous keys with a shared prefix. So you can think of it kind of like a tablet was in Bigtable, but now they have this notion of multiple logical tables being sort of interleaved. And so if you're not used to staring at this syntax, don't worry too much. But those of you who are thinking in terms of DDL in a relational database, they have kind of a create table language that looks like this. You create table users with 2 columns, and then you give it this keyword directory. And then you have a create table albums with some columns, and you have this keyword interleave in parent users. And what you end up with is something like this, where there's a user with all of its albums and a user with all of its albums. And so you can see here that what we've been talking about, all these different systems are experimenting with ways of getting these nested data structures, hierarchical data structures, that look a lot like what we saw way back in the 60s, right? And the motivation is the same as it was then. It's actually really, really fast. When you're going to access, when you want to pull up a user and then immediately pull up all of its albums, it's really fast to access this way, right? But I'd probably speculate that the reasons why the relational approach eventually replaced these, it can and will happen here as well, is that performance is not the number one priority a lot of time. It's minimizing the amount of developer headaches. Okay. So remains to be seen, but I think that this incremental walk step towards a big new scalable relational database is underway. Now again, that doesn't mean that I'm saying use all the old databases. They really were designed for sort of a different workload, and they really don't. There really is no evidence that they scale to some of these levels. But that doesn't mean that you sort of throw out all the everything we learned. Okay. But that's more me editorializing. So fine. So how this works is there's a universe master at the very, very top, and this is just a singleton. There's only one of these for deployments, and they sort of imagine there might be only one or two of these deployments anywhere. So they have sort of one for test, one for production/test, and one for production, and that's it. So many different applications will all use the same deployment of Spanner. And so this is mostly just status information about the zones. It doesn't interact with clients at all. And then there's a placement driver that's responsible for moving these directory sets of records around for load balancing purposes, and this happens on the scale of every few minutes. All right, and then within a zone, there's a zone master that assigns data to span servers, and there's a location proxy that sort of knows where everything is and routes requests to the appropriate span server, and then the span servers themselves serve data. And so in here, it's starting to look a little bit more like Bigtable. Zone is essentially an individual Bigtable deployment. Okay. So inside of a span server, this is where the big difference here is this is where they're going to try to support fully consistent transactions. So across these, within a group of these replicas, they support two-phase commit. This only is needed when a transaction actually accesses data that's across, that is not contained in one particular replica. Okay. Other than that, it just skips over this logic and it doesn't cost anything. Okay. And then one step down below this across. So this is, sorry, I guess I'm using the wrong terminology. So two-phase commit is across groups, and when the transaction only is contained in one single group, then you drop down a level and you run the Paxos algorithm that I didn't talk about in detail, but I mentioned exists, in order to sort out the reads and writes for, in order to handle the write. Okay, and then the only other piece I'll mention here is that this term Colossus is new. It's the successor to Google File System, and Google File System is the original term for the open source implementation of HDFS, which underlies MapReduce and Hadoop. Sorry. GFS is to MapReduce as HDFS is to Hadoop. So when I'm throwing these acronyms at you, that's how to keep it straight. Okay. So that's all I want to say about Spanner in particular. But just take a step back and look at all the different systems that Google has for a second. MapReduce was a paper in 2004 that had a ton of impact. Bigtable had a ton of impact, and then later there's Megastore. There's the system Tenzing that we didn't talk about, but it's a SQL system on top of MapReduce, much like Hive, if you were familiar with that, or if you remember me mentioning it. And then Spanner very recently. And so you can sort of organize these things into a timeline this way, just to kind of get a sense of this. And because these systems have had so much influence, I want you to be aware of what they are and sort of how they fit together, so it doesn't just sound like a big jumble of terms. So MapReduce was, one of the earliest ones. Wasn't quite the earliest. There's actually another one called Sawzall that didn't really get a ton of traction, but it was a nice paper. And then Bigtable came a couple years later, and I drew a dotted line there representing that they're sort of compatible or designed to go together. One was for MapReduce for analytics, Bigtable was for the sort of micro operations. And then both of these had, a few years later, had an open source implementation in Hadoop and HBase respectively. Okay. Fast forward a few more years, and you've got Megastore and Spanner coming very quickly, one right after the other. And this heavy blue line represents, it's pretty clear that the influence is fairly direct. In fact, I would suspect that there's a lot of code being borrowed. I mean, Megastore makes plenty of references to Bigtable, and Spanner makes references to both Megastore and Bigtable. And the papers have many of the same co-authors. Okay. And then MapReduce depends directly on, Tenzing depends directly on MapReduce. It provides a SQL layer on top of MapReduce. And then there's some other systems here. One is called Dremel, which was originally for very fast aggregate queries, but really just aggregate queries, but at extremely low latency. So this is, in the analytics camp, because you're doing these sort of aggregate questions as opposed to sort of micro updates. But it was extremely low latency, unlike MapReduce, which is more of a batch system. And so this is a great fit, and it's a very nice system. And in fact, since then they can do joins, not just aggregates. And more importantly, this was exposed as a service that you can just use directly over the web, even in your browser, called BigQuery, and that's an important one to watch. It's one of the few systems that is available as a service through as a cloud service, but scales to very, very large data and supports analytics. Okay. And then another one that we won't talk about yet, but we will come back to, is Praegle. And this adds the one secret ingredient that is sort of near and dear to my heart, which is iteration. And what I mean by that is when you run MapReduce jobs to do analytics, you're sort of taking step 1 and then step 2 and then step 3 and you stop. But for many kinds of tasks, especially in data science, many of these analytics tasks, these machine learning tasks, you have to do something again and again and again and again until some kind of convergence condition is reached. And Praegle and one of our systems and a few other systems are the ones that tried to notices this limitation of MapReduce and extend it. So people were doing this with MapReduce, but they do it sort of in fairly ad hoc ways. Okay, and so we'll come back to that and talk about it. But, analytics, low latency, micro updates. So those two big classes of systems, and then analytics with iteration is perhaps a third class of system that we'll talk about.